Just, people have been asking, Colonel, when is your band playing again? You'd be amazed at the number of people that ask me that on a daily basis. So my band, I play in a number of different bands, different formats, but one band that's been a lot of fun for me started it in January, is a band called the Threedles. We bill ourselves as the only three-piece Beatle tribute band. So we're playing at a club downtown called the Atlantic. The address is right there, 15 North Main Street. It's right at Ground Zero, Gainesville. And we'll be playing 2 sets of Beatles music. We'll probably start around 10. And who likes the Beatles music? Beatles? Any Beatles fans? If you know music, you like the Beatles. Anyway, so if you're, not free Friday night, want to see the Colonel do the other side of the Colonel, what I was really meant to be. I was born an artist. I wanted to be a hippie. My dad wouldn't let me. I wanted to be a musician. My dad didn't like that. Forced me to go to college, beat all the crazy notions of being an artist out of me. Like, imagine this. There's a spark on the ground. It's barely growing, and you come up with a big shovel and do this. That's what happened to my artistic ambitions as a child. So now, as I said, I wanted to be a hippie. My dad wouldn't let me. Well, there's nothing preventing me from being a hippie now. And so part of that is I'm coming back in contact with a big piece of me that didn't exist for a long time, and that is playing in music. There I am. I love pictures of me. And so it's the Threedles and a band I've never heard of called the Lifeguards. They play surf rock, apparently. So please, if you can see, there's only 15 people going so far on this Facebook event. Oh, there'll be lots of people there, believe me. But anyway, the Atlantic Friday night, loads of fun. But that's not what we're here to talk about. We're here to talk about acid-base chemistry. Oh. Look at that. You are among now about, well, there are 300 of you. You're among now a handful of people who have seen this. This is the back cover of my album, which I will release later this year. The album is called Dragonfly. And it's going to have a picture of a dragonfly on the front cover. But yes, I will have a CD release show, an album release show in December before the end of class. That's the way it's planned now. So you got to come to my album release show, my Dragonfly album. This is, what's that? Energy in Life. It's Energy in Life, exactly. There it is. This is my 6th album. It's my 2nd solo album. So I work real hard at this stuff. It's hard work being an artist. If you don't think so, you're not an artist and don't try. It's hard work being an artist. All right, but enough art. So, let's put the other hat on. As you know, wearing my scientific hat, I'm obsessed by the random walk. And I have my... Sorry. I always remember to turn this off before class. Today is the one day, and my dork friend from Colorado calls. Sorry about that. Quit now. No. Okay. So I'm obsessed by the random walk. And my favorite saying, molecules are like little hammers and they can pound other molecules into submission. And we gave an example of that last time when we talked about this group of acids and we found out that when we talked about bond strength, that one had the highest bond strength, and that one had the lowest. And what we're talking about when I say bond strength if we just call it HX, where X is fluoride, bromide, iodide, chloride, we're talking about the strength of this bond. Now, we draw a bond as a little dash, but we understand what that means. We understand that that's a shared pair of electrons, that a covalent sigma bond like that is a shared pair of electrons. And that bond strength increases as we go up. Now, what's that got to do with the random walk? What that means is, by and large, when a randomly walking H2O molecule goes slamming into that, that bond is strong enough that it doesn't fall apart. In fact, the Ka, I think, was on the order of 10 to minus 3 or something like that. So the idea that that would fall apart doesn't happen at room temperature because the energy of the random walk slamming into that can't beat that molecule into submission. But that HCl molecule with that weaker bond, here comes a randomly walking water molecule. Ouch! And that one falls apart. So it's bond strength more than anything else that determines how strong an acid is. And if that bond is weak, that acid will be strong. And if that bond is strong, as in the case of HF, that acid will be weak. And so it all gets back to this notion of molecules being like little hammers. And it's the randomly walking water molecule just hammering on these other molecules constantly. In the case of HF, the HF says, I'm strong, I'm a strong bond. You can't break me. Boom, bounce off like Superman. HCl, weak bond, therefore strong acid. And we can take that a step farther now and introduce this fun group of molecules, the oxyacids, OXY acids. And so we've already seen some of these oxyacids. Oxy means there's oxygen in the chemical formula somewhere. So obviously our pal sulfuric acid, who we've talked about now many times, oxyacid, oxy-acid. And our pal perchloric acid, obviously an oxy-acid. Many examples. Our pal phosphoric acid, oxy-acid. It's a very common motif now in acid-base chemistry. And we can do the same sort of analysis with regard to bond strength in a slightly different way. Let's make another series of acids. So we'll go name, dot formula. Remember dot formulas, right? Lewis dot formulas. Well, I'm not going to give you exactly the dot formula. Let's just call it the formula. And then strength. So, okay. So, there is hypo, chlor, hypochlorous. Now, I want you to latch on to this nomenclature. I told you learning chemistry is like learning a foreign language. You've got to learn vocabulary. 8 is an anion. Onium is a cation. Here's some interesting nomenclature. Let's go through the series. This acid is HOClO. Now, what that means is that's given a negative formal charge and that's given a positive formal charge. You note that O, in all the molecules that you know of, if you think about it, O is typically divalent, H2O. But here we have a situation with one bond sticking off of an O, and so that's got to have a negative charge. And likewise, the chlorine has an incomplete octet, or an incomplete inner shell. 1, 2, 3, 4, 5, 6, and it wants 7. So these are called formal charges. You learned about this in 2045. And what it's saying is that this simple notion of drawing sticks representing bonds doesn't work so well. But this is a weak acid. So now you look at this and you now are calibrated with the kernel's ideas about weak and strong weak acids, and you say, well, the kernel said sort of the garden variety weak acid has a Ka, a 10 to the minus 5. This is much weaker than that. 10 to the minus 8. Okay. Now. Now, we're going to get rid of the hypo. So I lost the hypo prefix. Interesting. And this one I can draw this way. HOCl. O minus, and that has a formal charge of 2 plus. And that is weak. And it has a Ka of 1.1 times 10 to the minus 2. Wow! You say, wow, that's cool. Just adding that other oxygen made the Ka go up by almost 6 orders of magnitude. So again, this is still a weak acid. The Ka is much less than 1. But on the kernel scale of weak acid strength, this is on the high side. So what did we learn? We learned that just going from 1 oxygen to 2 oxygens increased the strength of that weak acid a lot. And the key thing to latch on is this idea of the formal charge. The chlorine has a formal charge of 2 there. We can continue our series now. We can go to the next in the series is chlor, no ic. So no prefix, but we change suffix. And that, which one did I leave off? That we can draw this way. Hold on, did I get this right? Oh, I screwed this up. I'm sorry, I screwed up from the very beginning. This is easy for me to do. I screwed up right from the beginning. So let's try again. HClO. Now, I'm going to get there. The simplest way to think about it. Now, that's hypochlorous, 1 oxygen. And that's weak. Now we're going to go to the chlorous, 2 oxygens. I forgot the HOClO. Now, that's the one that has the formal negative charge there and the formal positive charge there. That gets a lot stronger, goes up 6 orders of magnitude. Now, we can continue our series with our pal chlor-ic. And it might be represented this way, HOClO, and it has a 2+ formal charge. And that one is strong. No longer a weak acid. And then finally we can get to the last in the series, per-chlor-ic. And that we might draw this way, HOClO. Oh no. And that has a formal 3+ charge, and it's strong. All right. A lot of things to learn here. First of all, what's it got to do with the random walk? Well, I said the random walk, whether the thing is strong or weak, is determined by whether those hammering water molecules can break that bond. And what you see, which bond? This bond right here. That bond, to make it an acid, it's got to break that bond. 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 So for these molecules to act as an acid, that OH bond must be broken. And so what we learn here is that in the case of hypochlorous, those randomly walking water molecules can slam into that molecule all they want. That bond doesn't break. Very, very rarely does that bond break. Very much a reactant-favored reaction to get that bond to break. So again, we go back to this notion that in the case of hypochlorous, hypochlorous, make sure I get this right, that HOCl, that bond's got to break for it to act like an acid. A randomly walking water molecule can slam into that all at once. It wants to. That bond is too strong. It doesn't break. On the other hand, this one falls apart real easy. You know that because this is a strong acid. As soon as it hits water, it gets clobbered by a randomly walking water molecule, and that bond breaks. So in the case of in the case of the perchloric, it would be the opposite situation. We can say what bond breaks? That bond breaks. And here comes a randomly walking water molecule. Slam! And boom, it falls apart. So whether an acid is weak or strong depends on the strength of that bond, the bond that holds the proton on. And that bond is being threatened and challenged and beaten constantly. In water, that bond is being threatened, challenged, beaten, bludgeoned. In the case of hypochlorous, you can get bludgeoned all at once. That bond is strong. very weak acid. In the case of perchloric acid, as soon as you hit it once, it gives in, it falls apart, and it dissociates. Now, why? And it all goes back to this notion of formal charge. And it all goes back to something I also stressed, and I'll continue to stress. You can understand a whole bunch of chemistry and physics and biology by just understanding electrostatics. What's that mean? Like charges repel, unlike charges attract. A huge swath of physics, chemistry, boils down to electrostatics. This is an example. Remember, we said that little stick that I've drawn there is not really a stick at all. It's a pair of electrons. And the oxygen and the hydrogens are attempting to share that pair of electrons, but electrons are negatively charged. And they see that 3+ charge and they say, it's like a vacuum cleaner. The 3+ charge is like a vacuum cleaner. It's sucking up charge density. It's taking that electron density. In order for that bond to be strong, there's got to be electron density. Those electrons that have to look like what I've drawn them, 2 electrons there. But with this 3+ ion sitting right next to it, that electron density gets sucked away. You can think of the electron density as being the glue that holds the bond together. And if you suck that glue away, then that bond gets weaker. So this issue of formal charge becomes very important. So this is strong because that electron density is being pulled away, but you'll notice there is no positive chlorine in that case. And so that bond is much, much stronger. That notion that the electron density is getting sucked away, it is a little bit, but not nearly as much. So again, we come back to this notion that we can learn a lot about acid strength by considering the strength of the bond that holds the proton on. And by looking at these chemical structures, you can make predictions about which bonds will be strong and which bonds will be weak. And as I said, those predictions are almost always based on electrostatics. The 3+ chlorine says, give me your electron density, and that electron density is the glue that holds the proton on. You suck that glue away, the bond falls apart, boom, just as I've shown over there. Now, so, final point that's fun for me is this issue of vocabulary. Note that we have a prefix and a suffix. Now, the first prefix is hypo. You know what hypo means. What's hypo mean? Beneath. Hypodermic syringe, injecting underneath the skin. Hypodermic. Hypo means low. Hypo means beneath. If you're hypoglycemic, it means your blood sugar concentration is too low. Hypoglycemic. Hypodermic. So that hypo means beneath. It means low. What's low? The charge on the chlorine is what we're talking about here. So this is the lowest charge of all this series of molecules. So we use hypo and us. Us also means low. Now you've already encountered this. In 2045, talked about the ferric and ferrous ions. Fe2+, ferrous, low oxidation state. Fe3+, ferric, high oxidation state. So you've already encountered this notion of us and ick before. But in this family, we're using them. If it's hypo in us, it's the lowest. So that's hypochlorous acid. Hypo us, low, low. Now, chlorus, no hypo, but an us, meaning low. So it goes from low, low to low. Ick means high, and per means high. So it goes low, 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 high, high, high. High, 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 high there. What's it talking about? One, it's talking about the formal charge on the chlorine, from the lowest one, 0, to the highest one, 3. It's also talking about the acid strength. It's also talking about the acid strength. High, high is a strong acid. High is also a strong acid. Low is a weak acid, but sort of on the strong side of weak acids. And low, low is a weak acid. So the name is telling you the chemistry. That's the cool thing for me about this series. The name is telling you what the chemistry is. The name is telling you which of these are strong and which of these are weak. Now, I got to tell you a story I always tell. When I took high school chemistry, I hated it. I didn't do very well in it. I took high school chemistry in the late 60s, and science were like establishment, man. That was like uncool, man. That was like working for the man. And so I wasn't particularly interested in the sciences. I was as a kid, but I was interested in poetry and creative writing, and I went to college as an English major. I'm not kidding you. I went to college as an English major. So I really wasn't into chemistry at that time, and so I remember very, very little of it. But I do remember this. My chemistry teacher in high school's name was Homer T. Caskey. He was your typical chem geek, like me, your typical chem geek. And he said, here's how you remember us versus ick. This is what it's the only thing Homer T. Caskey taught me, all right? Thank you, Homer. Here's how you remember us versus ick. You don't want to be up there with the icks. You want to be down here with us. That's how you remember ick being the high oxidation state. You don't want to be up there with the icks. You want to be down here with us. So I've always remembered ick and us from that story. I told this to my wife, and she goes, who are the icks? You're overthinking it. So that's how I remember us and ick. So we got a prefix hypo and a prefix per, and we got a suffix us and a suffix ick. And this us and ick in particular you see a lot in chemistry. So that's fun stuff about bond strength and the random walk and us and ick. You don't want to be up there with the icks. Be down here like us. Work for me. All right. A couple other fun things about acid-base chemistry. Okay. Let's talk about salts. Let's talk about salts. Another name for a salt is an electrolyte. Electrolyte. Another name for salt is electrolyte. What this means is you take a substance tell if a substance is a salt, you can throw that substance, here's your substance, you don't know if it's a salt or not. There it is. You throw it into that water, you shove 2 electrodes in it, and you see if you can measure a current. If a current will flow through that solution, that means there's ions in the solution. So that's the key thing that an electrolyte or a salt does. It releases ions to aqueous solutions. So that is a key thing to get in your head about salts. Salts release ions into aqueous solutions. And as a result, the solution will conduct an electrical current. And that's where the electro comes from. So it's called an electrolyte because you can test whether it's an electrolyte or not. Throw it into water and attempt to pass a current through that solution. If it passes a current, it's an electrical current. That's why it's called electrolyte. If that water will now pass a current through it, and we'll talk about this in detail when we talk about the last chapter, chapter 21, then what that means is that substance released ions. It's the ions that carry the electrical current. So ions carry electrical current in a solution, hence a salt is called an electrolyte. Now, you already know all this. And lots of examples of salts that we've encountered. Sodium chloride, strong electrolyte, throw it in the water, dissociates to 100%. So there are the ions, and if you measure the conductivity of a salt solution, you will see that it will pass an electrical current. It's because those sodium and chloride ions can move in an electric field in the solution. Now, that obviously is a strong electrolyte, meaning it dissociates to 100%. But we've also encountered weak electrolytes, or weak salts, I think in analytical lab, if you take sophomore analytical lab, there's almost always an experiment involving barium sulfate. And the key feature of barium sulfate is that it's a weak electrolyte. So we can think of strong electrolytes, weak electrolytes or salts. So barium sulfate's a weak electrolyte. We already talked about our friend silver chloride, also a weak electrolyte. So what that means is, for the weak case, the position of equilibrium lies very far to the left. It is very much a reactant-favored reaction. Nevertheless, it does release some ions to the solution. Even though in these two examples, the amount of barium and the amount of sulfate is small, it still releases those ions into the solution. So these are examples of what you might call inorganic salts. These are examples of inorganic salts. But there's inorganic, meaning there's no carbon in them anywhere. So, when you take organic chemistry, you say, well, what is it? I'm studying all these molecules and all these reactions in organic chemistry. What ties it all together? There's carbon in the molecule. So that sort of defines what organic chemistry is. Organic chemistry, in some ways, is the chemistry of carbon atoms as they combine to make molecules like benzene or benzoic acid. So we could take our friend benzoic acid, and we can react it with sodium hydroxide, and what do we get? We get a salt. So, while you haven't probably thought about it much to date, most of the salts you've seen so far are inorganic, but you can think of a huge host of organic salts like this. So this would be sodium phenolate. Take, this is phenol. It's a weak acid, in fact, very weak acid. Yeah, we haven't introduced phenol yet. This is our friend phenol. OL. If you take organic chemistry next semester, OL means alcohol, almost always. So phen from the benzene group is often called a phenyl ring. This is called a benzene group, often called a phenyl ring. Another name for a benzene group, phenyl ring. Got it? Again, this is vocabulary. What? Everything I say can be on the test, including my bands and everything. Just kidding about the bands. There will be no band-related questions on the exam. So phenyl ring, phenol, a phenyl alcohol. React with sodium hydroxide, you get a salt. Organic salt. Lots and lots and lots and lots of examples of organic salts. Now, with these inorganic salts, yes?
Why is that salt and not water?
Oh, sorry. Very good. The hydroxide plucks the proton off to make water, leaving a salt. Sodium, phenyl, 8. Look at that. Anion, 8. Vocabulary. Now, when we talked about the inorganic salts, we typically find out that these salts don't affect the pH any. You throw sodium chloride in water, the pH doesn't change. Now, why is that? Just taking sodium chloride as an example, so now we're going to address this issue is, can salts change the pH of a solution? And the simple answer is inorganic salts, let's put it this way. Sometimes organic salts, almost always, So how can a salt affect the pH of a solution? Well, let's take this example of sodium phenolate. We know that phenolate is the conjugate base Sodium phenolate is the conjugate base of the weak acid phenol. So if we throw that sodium phenolate in the water, here's our sodium phenolate, solid, we throw it in the water, we get the salt does its salt thing. What is its salt thing? Releases ions to the solution. So that's step one of what sodium phenolate does. It does its typical salt thing. You take that, oh, I'm sorry, this H should not be here. Throw that molecule in the water, it does its salt thing. It dissociates. It gives you some of the phenolate and some of the sodium ion. But this is where it gets interesting. This is where it gets interesting because the phenolate, as we said, is the conjugate base. So that phenolate, once it hits the water, can act as a base to regenerate phenol plus OH minus. So there's our first example of a salt that affects the pH of a solution. The salt affects the pH of the solution because the anion of the salt is a weak base. So yes, you throw the salt in water, it does its salt thing, it dissociates into phenolate and sodium ion, but the phenolate is a weak base. So it can do its base thing, react with water to regenerate phenol and OH. So you throw sodium phenolate in the water, the pH is basic. You get a basic solution. Now, we can think of other examples like this. Here's an interesting salt. Ammonium chloride. So again, let me just write this down. In this case, solution is basic. Now here's another salt, ammonium chloride. Draw the charges on it just to make it clear. Throw it in the water. It does its salt thing. It releases ions to the water. Now, but again, we know that ammonium is the conjugate acid of the base ammonia. So another thing can happen here. The ammonium that hits that water can react with water to give you back ammonia plus the hydronium ion. So here's that was an example of a salt that gives a basic solution. This is an example of a salt that gives an acidic solution. And so the key take-home message here is that if a salt is composed of cations and anions, like all these examples that we put up on the board here, cations and anions. If one of those components is a weak acid or a weak base, these two examples give an example of each, then that salt's going to change the pH of the solution. Now we can contrast that to the salts that we're more familiar with, the inorganic salts, and that doesn't happen with the inorganic salts most of the time. So the take-home message, let me just write it down, is that's the take-home message right there. And that can be contrasted with our simple inorganic salts. So simple inorganic salts like sodium and chloride, sodium chloride, throw it in water. The cation is not an acid. The cation anion is not a base. And so no change in the solution pH. So you throw sodium chloride, potassium chloride. You can think of perchlorates, potassium perchlorate. Same idea. We already talked about our friend perchlorate, or perchloric rather. Perchloric, per high, ic high. Same thing applies. Perchlorate is not a base. Potassium is not an acid. So that won't change the pH of the solution. But we'll say this final thing. There are some inorganic salts that will change the pH of the solution. So the take-home message is for almost all organic salts, you throw an organic salt in, it's probably going to change the pH of the solution. Inorganic salts, a lot of them don't, like these, some do, and we'll talk about the ones that do on Friday.